Ora si registrerà la conferenza.
Buongiorno a tutti, ben collegati. Oggi giovedì 22 luglio, sono le 4 di pomeriggio e andiamo con l'ultimo webinar prima della pausa estiva. Webinar che teniamo in collaborazione con SIGLENT, molto interessante. Ricordo che l'evento sarà registrato, quindi sarà poi comunque disponibile per essere rivisto o eventualmente condiviso con i vostri colleghi. Io sono Gianmarco Moroni, presidente di Butterfly. Per chi si volesse collegare con me lo può fare tramite i link qui sotto. Per chi ci conosce o per chi non ci conosce, Butterfly è un'azienda ormai storica nel settore della strumentazione di misura, fondata nel 2002, siamo praticamente dietro l'aeroporto di Bologna, Calderare di Reno. Siamo un'azienda totalmente autonoma dal punto di vista appunto delle vendite, il marketing, amministrazione e logistica. Abbiamo una copertura nazionale per quanto riguarda l'attività, diciamo così, presso i clienti B2B e accademici, e grazie al nostro sito dal 2013 ormai siamo in grado di vendere e spedire in tutta Europa. Siamo principalmente attivi nei settori della ricerca e sviluppo, nella produzione elettronica, enti di ricerca e didattica, enti governativi, aziende che si occupano di fare manutenzione di impianti industriali, e sempre grazie al sito siamo in grado di fornire parte del catalogo anche all'utenza privata, cioè coloro che non hanno la partita IVA. Per semplificare abbiamo, diciamo così, diviso l'offerta in due macro gruppi, uno che si occupa di sistemi di misura, soluzioni pre-compliance, EMI e termografia, e uno invece che si occupa della parte di protezione antistatiche e di saldatura manuale. Come molti di voi sanno, siamo gli importatori per l'Italia e per altre nazioni europee dell'azienda giapponese Acco. L'ho tenuta molto corta proprio per dare spazio a Thomas di fare la sua presentazione. Io ho già visto l'anteprima, è veramente molto interessante. Teniamo le domande eventualmente per la fine. Vi chiedo di gestire il vostro audio in autonomia tenendolo spento. E ora passo la parola a Thomas. Thomas, you can activate your audio in modo tale da poter partire con la presentazione. Ciao Thomas, good afternoon.
Hi, Gianmarco. Hi.
So you should have a pop-up on your screen now.
Yeah.
Perfect. So have a good webinar. I'm here to support you in case of needs.
Thank you very much.
Thank you.
So I'm starting. Do you see the presentation now?
Yes.
Very good. Thank you, Gianmarco, for the introduction, and welcome to everybody who is spending the time 4 o'clock in the afternoon in the summertime. So today we are talking about RF components and mainly about vector network analysis. And one second, I have a little. Okay, yeah. My name is Thomas Rottach. I'm responsible for sales and marketing in Europe at SIGLENT Technologies. And for all who didn't come across SIGLENT so far, we are a test and measurement equipment manufacturer. Our headquarters is in Shenzhen, and we have a subsidiary in Europe where I'm located in Germany, and we have a subsidiary in North America. The complete overview on our equipment which we offer today is oscilloscopes up to 1 gigahertz and function generators, and then arbitrary function generators with 500 megahertz, and RF function generator or RF generators up to 6 gigahertz. DC power supplies, multimeters, spectrum analyzers, also as RF real-time analyzers, and also with vector network analysis included. And since 2 days, we also have a VNA vector network analyzer with 2 full port. Okay, so let's start with the general presentation. So I will do a quick introduction, and after this, I will talk about a little bit of 5G and the impact of 5G, the arising challenges and tasks, as well as some VNA basics in order to understand and to get a little bit better insight about accuracy and how we can secure the accuracy. We talk a little bit about measurements and end with a quick summary. I would like to start with a number. It's 20 exabyte. I come across this number when I was investigating a little bit about data traffic in the last days. So it is an 80-digit number. I've found this quite interesting, and I digged a little bit into this. And the 20, let me just activate my pointer, my marker, or even the annotation. So you see, this was the 2018 data traffic monthly worldwide. So this is a really impressive number, I think. And today, 2020, we should have around 40 exabytes per month worldwide. I did also some research on this, and I found that the estimate, which was in the Cisco report in 2019, is quite close to the reality now. So this means within 2 years we had a doubling the amount of data traffic, mobile data traffic. So there is nothing landline stuff included. In parallel, also there are some interesting developments from smart devices or non-smart devices. So you see it's continuously increasing. So from 50% up to 75% roughly in the next 1 or 2 years, we should reach this kind of number. So why I'm talking about this, the interesting part is that it is estimated that 5G will also push this even more and ahead because of some additional possible applications which can occur. Smart devices will have faster data transfer rates, and it will be faster in general. There is also an estimate: the faster the devices are and the faster the connections are, the more data is consumed by users. So this will push it upwards. With the coming releases of 5G, there will also be more IoT devices, so machine to machine. There is also the part with the wearables. So also in the medical part, there will be a huge growth. Also, there are some new applications like virtual reality and augmented reality, which are very data consuming. This is also something which will push the amount of data traffic even higher in the next years. At least it is expected that this will happen. If we look at the 5G in general and which market will be or will face the most or the biggest disruptions, then there is clearly the expectation that the automotive market will have the biggest impact, or the 5G will have the biggest impact. It's mainly also because in the direction of automatically driven cars or self-driven cars, all this kind of communication, V2X, so the car communicates with other cars, with the environment around, with walking, cycling, people around, they all have mobile phones, everything could be connected to each other. And this kind of data traffic and will be also an enormous part. Also cloud services and the machine-to-machine stuff with the data traffic in the machine-to-machine and automated and smart factories. This will be very big part. What about the status on 5G? This is a map from mid of 2020. We are today mid of 21, and we see that the standardization is almost done for the release 16. Release 16 I will explain later, and release 17 is also a little bit shifted or a little bit behind because of the COVID, but it's not far behind. So all is more or less ongoing, and the evaluation is working. So the interesting parts for release 16 and 17 coming more or closer to us, or closer to everyone. So with release 15, so the initial 5G release, this was focused on extending the mobile bandwidth and getting a bigger bandwidth for also data transmission, also on the mobile side. But release 16 has some quite interesting parts, which is the ultra reliable low latency communication. The definition of this is the key or the base for self-driven cars or automated driven cars, because you can't live with delays or something like that. If you have something automated, also for the factories, this is very important that there is no latency between commands and inside the communication. So this is most important. I mentioned before the V2X, the standardization on this is also part of the release 16, and release 17 is mainly focusing on the mass machine type communication. So this will push the IoT market, and there are special channels for IoT. It is called NR Lite, so new radio light, specialized channels and specialized setup for IoT. All these IoT devices typically have very low data rates, and they're sending not all the time, but we are talking about billions of devices and billions of connections over there in altogether. So what kind of challenges arise here? What we see is we're moving also into higher frequency. In the 5G, there is also the FR2, the frequency band in the 26, 27 gigahertz range, also above. This is also the reason for covering or for getting into this high data rates, or also in the bigger amount of data traffic. You need bandwidth and you need the channels, and they are looking for free spaces in the spectrum, and also this is one of the ideas. Also with the higher frequencies, it's possible, of course, to allocate higher bandwidths for the modulations and for the communications. And this then leads to also higher data rates. With smaller device is also the higher the frequency, you can size down everything. Of course, the reach, the higher the frequency get, the reach will become shorter, but this is also one of the challenges, how to have medical devices working efficiently with efficient battery power and being connected all the time. The other part here is the security, the IT security, but this is not my topic today, but this is generally one of the big topics about this IoT and all this data transfer, what we have. And another challenge is that we have much more senders and receivers, so susceptibility against each other, intermodulation, also interoperability is one of the challenges and the interesting tasks which have to be solved. And massive MIMO, so multiple input, multiple output, means you have not a single antenna, you have 4, 8, 16, or if you're looking at 5G, the antenna arrays, there are 64 or even more antennas aligned, and you can create kind of beam forming to address or to have a real beam to the user, and therefore you need a very accurate alignment of the single antennas and also of the signals in the background. So all this phase shifts and everything has to be very accurate. And this is the general problem or the general task which comes up is the higher the frequency get, the higher the data rates are, the more important is it that everyone is aligned perfectly. And at the back or at the ground of everything, there are just the components, and also the components, of course, have to satisfy certain standards. But finally, if you look in the data sheets, typically data sheets don't cover every application or every scenario which they are in use. So there is really a strong need to do evaluation on components very accurately and very often in this case, and to be sure that the whole system works together. But this is the part about the basics. So how we can measure components and how we can determine characteristics of devices. If you break it down to the simplest basic idea, then it's you use an input signal which you accurately know. You feed it into your device and you measure very accurately the output, and then you can determine what your device is doing. So you see either you have a gain or attenuation at a certain frequency, or you have a phase change, depending, of course, on the device. And with applying a sweep, then you can create all this kind of information over frequency. But before we go a little bit more then into the details about the measurements, there are some prerequisites we have to clarify at the beginning. So in the RF world, we typically are in the 50 ohms environment. This is very, very strict in this case. And why we are at 50 ohms, that's one of the questions I often hear is, or the reason is that there was two guys in the Bell Labs some years ago, some 10 years, 100 years, I'm not exactly sure, but they had to do or to plan a transatlantic line, communication line. And they were thinking about what is the best material and the best diameters and the best setup for this. And I figured out that the best power capability of the cable is if it has 30 ohms. And on the opposite side, the lowest attenuation of the cable appears at 77 ohms. So this leads them to go into the middle of both to get the best of both sides. So then they choose 50 ohms, and this became the standard for all the communication systems we have. There is an exception, so everything which goes around with television and satellite television, all this kind of stuff. Here we have typically 75 ohms. The reason is quite clear, because the lowest attenuation is at 77 ohms. And if you think about satellite receivers, the signal which comes is not very, very powerful. So it's very weak. So it's more important to have a low attenuation than a very good power handling capability. It's also important to know that the standard impedance is a function of the dimensions of the line. So you see the coaxial and the waveguides, and also the coplanar and the microstep. So this depends on the dielectric and the inner diameter, the external or the outer diameter, and space between the lines and all these kind of things. The second prerequisite is the power transfer efficiency. To explain this in detail, it means if you have a source which has a source resistance and you have a load resistance, the highest normalized, in this case, normalized the highest power comes up at the load at this point, which means, which means we have the load resistance is equal the source resistance. This is what we're trying to aim and achieve in every RF system. So you have 50 ohm as the nominal impedance, and we always try to keep in this range and to keep consistent as possible. This is also valid for the complex impedances, but you have to see, or you see the imaginary part has to be in the opposite, so minus and plus. So this X out so that finally you come back to RL equal RS. Okay. So to make it a little bit more visible, I choose a kind of river, which is 50 meters wide. We have a certain defined level. I chose 50 meter because of the close relation to 50 ohms. And what we have now, we fill in the gap also a 50 meter wide channel, and we see everything fits together, everything works. So we are at the point where everything works and everything is fine. So the whole water will be transmitted without any issues. So if we looking into a vector network analysis, this typically is the transmission measurement. So you say, okay, from the port 1 to port 2, and in this case, everything is aligned to 50 meters, 50 ohms, and everything is fine and works smoothly. If you transfer this picture on the transmission line and you say, okay, at the end I have a match, so it means the Z0 here is also at 50 ohms, then you can say all the energy from the source is running through everything and is ending up in the Z0 and will be there. If you now think about having an antenna there instead of a resistance, and the antenna is perfectly aligned and perfectly switched, all the energy which comes from your source will be transmitted and transferred to the air. This is exactly what you want to have. So you don't want to have losses on the cable or anywhere else around. So zero energy is flowing back or floating back. So what happens now if we change the DOT? In our case, if we reduce the width of the river from 50 to 30 meters, so you finally see we have problems here or reflections here, and we also have problems on the other side, on the opposite side. So this can be considered as energy loss if you look into the amount of water which flows from left to right. And there is also the point to measure it is the reflection. So we are interested in the part which comes back to the source. This is what in the network analysis called S11. So that's the reflection on port 1. Of course, if you turn the whole picture around, there is also a S22 and a S12 for the transmission and the reflection. Again, transfer this to the transmission line. We now have no matching device. So we have the 25 ohms as load resistance, and we see there is some energy coming back from the non-matching device on the backside, and then it creates standing wave ratios or standing waves, and you can of course then calculate the ratio and SVR and stuff like that. That's very common and very well-known measurement in this case. If we go to the extremes, so we have a short, which is 0 ohm, or we have an open, which is infinite, then we see the wave is fully reflected. So this means all the energy which comes to the short or to the open will be completely reflected. The point is that the open reflects it without a phase shift, and the short reflects it with a 180-degree phase shift. So this is important to recognize and to keep in mind for later, because this is also part of the procedure which we use when it comes to calibration. So how a typical setup at a VNA would look like. So we have two types of measurements. That's the transmission and the reflection. That's what we shown before with the river example. So we have the S21, so we have a source included, and the signal runs through the VNA to the output port. It goes through the device under test and it comes up at the receiver B. During the time we measure here the reference, so this means we relatively know what we are sending. This is what we want to achieve, of course, what I mentioned at the beginning. We are comparing a known signal with the receiver signal or with the outcome of the DOT, the output. So that's one part. And if you're looking one step ahead and you're measuring the reflection, the reflected part, then it's also the same. The green line, it goes down here, and the reflected, which happens if there is not a 50 ohm, then it comes back to the receiver A, and then of course you have the reference before, and then you measure here, and you can determine between the receiver A and the receiver B, or the reference, sorry. So that's the two measurements, and that's the complete setup. If you're having a 4-port VNA, you typically have exactly this configuration doubled, but it's also linked together because you can also measure from port 1 to port 3 or to port 4, of course. So it's not as easy as just doubling it. It's a little bit more of connections, but in generally, the idea of having 2 receivers per port and having one source per 2 channels or 2 ports is the same and is similar. So now we are ready. We can start measuring. Are we? I would say no, because we don't know anything about our system itself at the moment. So up to now, we think about that our channel means our path inside the instrument is quite clean and quite perfect, but in reality, it's far away from being perfect. So you have inside the path, you have reflections, you have delays, you have losses, you have crosstalk between ports. Also, the output port is typically not 100% 50 ohm, so there is a small mismatch as well. And you also have distortions on these sides. So how you can determine your device works if you don't even know how your own channel is looking. So the point is now that we have to identify where are the sources come from, where are the problems. So we have some types. So the first is we have our source here on the left side. Maybe I'm switching to the pointer. So we have the source here, we have the reference receiver, and the signal goes to the device. So we also have already a directivity between the 2 receivers. So the reference receiver and the measurement receiver. We have the source mismatch, what I showed with the river example, on the load mismatch on the other side. We also have crosstalks between the ports. There is reflection tracking A to R and B to R. So these are the typical sources. So this means per direction, we have roughly 6 error terms. So this means in total, we have 12 error terms for a 2-port device. And in order to be able to solve this, we need to do measurements with known devices. So means we typically, I guess, if you're working with VNAs, you have ever heard about the open, the short, the match, the through calibration. This is exactly what we are doing. We're comparing the source or the signal we are sending from our source with with a solution or with a device under test, which we exactly know. So we bring it back to a known standard. And with this, we can learn what is not perfect in our sender path or in the receiver path, and how issues happen. And then we can, as soon as we know this, then we can determine exactly what the device looks like and what the device changes and how the device performance and characteristics is. So for the calibration, I said we learn about the imperfections of the analyzer and the test setup. We measure everything very accurately, we store everything accurately, and then we put everything into a big mathematic package, and then everything will be solved, and we can come for accurate measurements. This is the first part. There are of course random errors, so they are unpredictable. Just think about if you change the device, so you have multiple devices, they're all, let me say they are all filters, all the same filter, and you want to compare these filters against each other. And even opening screws and closing screws might create random errors in this case. And this is something you cannot avoid. You cannot avoid with calibrating or recalibrating. So this is really something, yeah, we have to live with it, but in generally we should roughly know about it. If we having drift errors means, especially here now in summertime here in our office, if I would do a calibration in the morning where we have here 18 degrees with open windows, and now in the evening we have 25 degrees here, there will be a temperature drift. And if I did the calibration in the morning, honestly, I should do it again to compensate everything. This can also be fixed and eliminated, but this is something you have to consider and you have to think about, depending, of course, how accurate you want to measure. Here is the error models in the full beauty, and you see there are 12 different definitions of errors, and with certain tests and calibration steps, you get some results and data, and then there are 12 equations, and the 12 equations can be solved so that at the end every error which is defined here is known, and as soon as this happens we are ready to go. What is a typical calibration procedure? I mentioned before we are using well-known standards to do measurements. So in this case, we're having a source, we're going down to an open. We exactly know an open returns full energy. So we know what we're sending into the system, but we receive something different. And with an open, we also have a 180-degree phase shift. So we get the information how much phase shift is inherent in the system and how much attenuation or losses or frequency response over the frequency do we have. In comparison, with the full reflection in the open is 0 degree phase shift. With the short, it is 180 degree. So we do exactly the same measurement. We do it again. We can combine these two results to get a view from both angles and determine more accurate the errors. Typically, the third part is that we use a very good match, so a 50 ohm match. So this means we expect 0 reflection. This means everything what we measure must come from either a crosstalk issue or maybe from inaccuracies on the 50 ohms inside the unit. This can also be accurately measured and stored and put into the equations. And also for the through, we have a very well-known through, so we exactly know what we have to expect on the opposite side, on the receiver B, and we can then, with all this kind of measurements with the standards or against the standards, we can determine and solve the error equations, and then we have a full calibrated setup. And then the next step is that we can start accurately measuring our devices and characterizing our devices. Are we now completely safe? Not 100%. So there are some exceptions, especially if you have a device which has a very high insertion loss, and if this insertion loss is higher than the typical crosstalk of the VNA. So typically this is 100 to 120 dB, which is defined as crosstalk, and this just happens on high isolation devices. Means if there is a switch in between, which is open at a certain state inside, then of course nothing comes back, and then you have issues, and then you have to do isolation calibration, because the normal calibration does not cover this high isolation part. Or you have very high dynamic range devices, like the filter we have here on the right side, which has a 125 dB stop band, and this then already comes into the critical measurement region. To solve this, there is a possibility of doing a specialized isolation calibration. Of course, everything good brings also something bad. In this case, we are working very close at the noise level of the analyzer. Of course, this has to be considered also with the measurements and inside the system and the complete error model. We have to use a lot of averaging to smooth everything out and to get clean results, to be able to do also this isolation calibration properly. And then it depends on the device with the crosstalk isolation calibration, if you use a two terminations or just one termination and the device termination. For the crosstalk, as you see, in the case of the filter, you have the region where it in the passband. So passband means all the energy comes from here, goes through the passband, goes to the receiver B. So everything is good. If it's well calibrated, a lot of energy comes through it, easy to measure or relatively easy to measure. In the stop band where almost nothing comes back, and you want to determine exactly how good is the stop band, then this is exactly the case where you see the crosstalk or where the crosstalk between the receivers might have an impact on the measurement. So you have to be sure that you measure the device and not your analyzer. So that's the background for this. So finally, after setting up everything, we know how the VNA looks like, how it is set up. We have calibrated it in a proper way. We know what we want to measure. So now we can go for this input versus output signal calibration or measurement or comparison. So now we come back to why we measure at all. So right at the beginning, I told you this highly increasing data rates and everything getting tighter and everything getting smaller and everything has to align much more to each other. This is the main reason why we have to increase the measurement capabilities and also why we measure more and very accurate in this case. So this is the modern systems. The base of everything are the components. The better that we know the components, the better we can set up everything. And building networks, we also have to characterize the networks to achieve systems and good systems performance at the end. Typical measurements for two-port, is gain, linear phase, all this kind of well-known measurements. And the impedance match, what I explained also extensively at the beginning, is a very important part. The more or the better everything is matched, the more energy flows through it, the less disturbances happens. And this is where we're aiming for. Regarding components and network behavior, in general, we have to divide or differentiate between two main directions. So one is the linear behavior. Linear behavior means just changing amplitude or phase, but not adding any frequencies or changing any frequencies. And we have also nonlinear behavior, which might generate additional harmonics and output frequencies, which in some cases we want to have if you think about mixers, but in other applications, like if we look talking about amplifiers, we don't want to have this. How this looks in detail. So on one hand, we have input, the time base, that's kind of sine wave. It's not a sine wave. It's more a rectangular. So consisting of the harmonic, the third and the fifth harmonic and the baseline here. If we put this to a linear network, which has an characteristic like filter, then we see at the output side in the frequency that the baseline will be attenuated very hard, very strong, and also the fifth harmonic will be attenuated. And the middle one, so the third harmonic, can pass almost unchanged. If you then look in the time domain on the outside, you don't see anything which has something in common with what you input at the beginning. Especially at digital communication systems, this might be an issue, and that's also the reason why you want to measure the linear and want to know how this works. If you're looking in communication systems, of course, filters are used to reduce additional frequencies out of the transmit band. The same behavior can happen if you have a linear network which has a flat magnitude, so there is no filtering, but you have a phase change over the frequency. So this means if you input again the same signal as we had before with the two harmonics and the bass, then you see it has here a 180-degree phase change of the third harmonic. Also, again, the resulting curve has almost nothing in common with what we are inputting here. So this is something to consider and something to measure. So that's the reason why we measure magnitude and phase, for example, of networks, to be able to determine what is the input, what is the output, and does everything work properly together. If we're looking about nonlinear transfer functions, in this case, we have something like an amplifier. You see on the lower part, the amplifier has a linear part. And when it comes to saturation, it moves into a nonlinear region. If your input frequency and input power now appears exactly in the nonlinear, then your inputted sine wave here will be disturbed. What you see here on the right side in the time domain view. If you're looking in the spectrum, this will generate harmonics and subharmonics, which you typically also don't want to have because it's also kind of energy loss, because you have then to filter it out again and all do this additional efforts. Also, an important measurement when you're looking about or testing with Vnas. What we are testing in general, so all the components, of course, we have it here in the middle, the capacities and inductivities. The important part for these components is that you have to consider that a capacity has different behavior if it is biased or not, and also on different voltage levels. The data sheets don't tell you this exactly for your application. With Vnas, which have an external bias T for DC, you can measure this and you can exactly determine how the capacity looks like in your special case. It's also for inductivities with the current which flows through. It also changes its values and behavior. For filtering, of course, it's important to see where is the stop band, where is the frequency, where is the center frequency, how good is the stop band attenuation, is there a pass band, where is the pass band, how much is or how low is the attenuation in the pass band, is there a ripple on top, a group delay, is there a phase shift, do we have, what else do we have, frequency response, we already had. Yeah, the input and output impedance, so how close is it to the 50 ohms definition inside the passband. For RF amplifiers, I also told you input-output impedance. Input impedance is extremely important because if you're coming from a 50 ohm and you're not matching with the input impedance of the amplifier, then energy will be reflected and don't go into the amplifier, so you're losing energy. So you have to input more energy to get the result on the output, which is an energy loss. And lost energy finally returns, if you're looking at battery power devices, the more power you have to input, the faster the battery is empty, and then you have to recharge or change battery or do whatever service activities. It's also something you don't want to have. Additionally, you need to know how much is the gain, how is the bandwidth, at which frequency you have which gain. The 1 dB compression point, this is the point where it changes from the linear to the nonlinear behavior. IP3 is also going in the same direction about linearity and nonlinearity. For mixers, of course, the important measurements are insertion loss, conversion loss, and isolation against the local oscillator and between input and output. For circulators, you measure typically isolation and impedance. And of course, antennas, we had the example where we had the matching at the beginning. You want to have a good match of your antenna to your amplifier, which is typically in front of it, or the filter, which is in front of the antenna, in order to transmit the most energy and to have the best connection to the outside world. If the matching don't fit, you can create, of course, matching networks. This is also something what you can do with Smith charts. The example, to keep the example of antenna matching, we have a 50 ohm environment. That's our target. We measured our antenna and found out that we are not matching. So finally, what we can do is, of course, finally stop. One tip here in between is, if you do antenna measurements, you have to be careful to do it in the right way, because also if you connect the antenna directly to the port of the VNA, for example, you have to consider that the VNA has a lot of shielding and a lot of metal plates inside, and these are all acting as kind of capacities, inductivity, which impacts the antenna performance and impacts the antenna impedance. So you see the two pictures here on the lower part. The left side has the antenna was directly connected to a VNA, and the right one was the same antenna was separated from a VNA. So this means be careful, use a cable or a chamber. If you have a chamber, then you're it's the best case, because you can separate everything. If you don't have it, then you separate it. You can use a coax cable in between, and then you do calibration to calibrate also the cable impact out of your measurement, or a test fixture. You can also test fixture de-embedding and embedding with VNA. So this also helps to do proper measurements and to avoid this kind of mistakes you see. It's a frequency shift, and it also looks a little bit different in shape. Finally, if you have done the right measurement of the antenna itself, the impedance, and you want to match it, then you can create, if you can't change the antenna because you have bought it maybe from whatever vendor and you get it into your system, or you want to have it integrated in your system, you can have a small antenna net or matching network, which can be created while doing or making a Smith chart measurement. What you see here is we have the match in the middle. That is very, very close to 50 ohms. And if you're looking at the reflection, then you see there is, at the point where we are very close to the 50 ohms, we have very low energy reflected and measured. So that's exactly where we want to be. For RF amplifier characterization, I mentioned before, we measure input impedance, output impedance, the reflections, and also the transmission interface, for example. These are the main ones which you can do at once. Typically, modern VNAs can also have much more windows. Our SIGLENT one can have up to, I don't know, 64 windows, which is very huge, and you don't see anything in real. But 16 or 8 windows are quite common to see, and you can have everything once connected, once calibrated. You set up everything once, and then you can combine and measure everything step by step, and you get all the data out of your system, and you get it into your simulation, or you get it into your design software. Then you can go ahead and optimize your system. I also talked extensively about the 1 dB compression point. So on the left side, we have the explanation. So we have an input power versus the output power. And at the point when it comes to the compression, then the output power can't follow the input power. So you make 1 dB steps maybe, and then you see at a certain point the output power leaves the ideal line. And the 1 dB compression point is when the difference between the ideal line and the measured line is 1 dB. This is what we see here on the right side. So on the x-axis, we have the power which we sweep, and here we have the measurement and the amplitude, and you use a reference marker and you sweep it, and then if the reference marker goes down to 1 dB, then this is the point, and then you see exactly, okay, that's the that's 11.5. So what is this? Minus 14.6 is the point of input power where the 1 dB compression point happens. So if you are in a complete design and you are setting up everything in the linear range, then you see it here. You input your signal, your modulated signal coming in. It's amplified. It comes out of it with higher amplification. You see also the constellation diagram is fine, and you see there is no shoulders in the signal. The eye diagram, all the eyes are open. In comparison to this, if you are setting the input power too high and you're reaching the 1 dB compression point, means you're moving into the nonlinear range, then you see immediately a degradation. You see the shoulders coming up, you see the eyes are closing, and you also see the constellation diagram. Everything moves away. So this is, if you're thinking about a communication system and your sender has disturbances on the neighboring channels, this also might impact the certification, and also it will disturb the neighboring channels, and that therefore the system will not work properly, the whole system. And also the data transmission, if you look in the time domain, bits can't be recognized in a good way, and the transmission and the data transfer is bad. Again, the higher the data rates and the faster everything becomes, the more critical is that everything is clean and everything is as perfectly aligned as possible. So it's quite important to have a well characterized amplifier. If you want to look at your transmission lines or cables and connectors, there is also a possibility to use VNAs in the time domain. So you see here a time domain screen. So we have it. That's just a cable, just for the better explanation or better visibility. With the first connection, the energy travels back and comes back to the input. So that's the lower part, and this is also the impedance, the input impedance in this case, the output impedance in the time domain. If you're looking at high-speed digital lines, it's very often common to use eye diagram measurements. So with this VNAs, you can also set up masks, and you can create and define the standard masks. And what you see here, you can define the stimulus. You say, okay, what is the input? What is the output? What is the data? Is it random data? What kind of data is it? You can also adjust it on the outside. And then also you get a quite good idea about your transmission lines on your design. And then you're able to determine if it works, if the eye is open, if the mask's not hit, and everything can be, or the data can be transferred as expected. As a summary, what I said at the beginning, we have a quickly growing demand for mobile data. There are new applications coming. Everything moves into higher ranges. We are getting more and more IoT devices with low data rates, but billions of devices. Everything needs to be optimized, systems, networks, and to be able to do this, you need a lot knowledge about your components, how they are working in a certain and specific environment. And finally, accurate and flexible measurements becoming more and more critical, and also vector network analysis in general helps to keep pace and to be able to solve the issues and also the coming issues. The second and last advertisement block is our new VNA. So we introduced it 2 days ago. This is the first full 2-port and 4-port VNA from SIGLENT. It goes up to the 8.5 gigahertz. All the screenshots which I showed through the presentation, or almost all, came from this instrument. Here is the quick summary. 2-port, we have 2 versions, 4.5 gigahertz, 8 gigahertz. The rest is very capable, state-of-the-art, the built-in web server. We have a very low footprint with a big screen. This is very good. It saves space on the desk. This is wonderful. It's for someone who is interested to have it on his desk. Also, the air is quite low, or the air, not the air is low. The ventilator is silent. So it's definitely no issue to have it in the lab. Yeah, the rest is all the types of measurements. And if you're interested, or if you want to have more information, Gianmarco and me are ready to answer questions.
Thank you, Thomas. Thank you very much for this presentation, for the introduction of the new series of analyzer. Ok, il webinar è terminato. Se c'è qualche domanda da parte vostra è il momento giusto, se volete scrivere in chat o se volete attivarvi l'audio e fare le domande. Vi ricordo che l'evento è in registrazione, quindi viene registrato e vi sarà poi inviato il link per poterlo rivedere e condividere con i vostri colleghi eventualmente. Ok, sembra che non ci siano domande. So, no question, good question, Thomas. Thank you very much for your time, and I close the room. Grazie a tutti, buona giornata, buone ferie.